So consider this is a generalized linear passive bilateral network. So any general linear passive bilateral network. So this network may consist of resistors, capacitors and inductors. So this is a circuit like an RLC series circuit or RLC parallel circuit. So that is an example of a linear passive bilateral network. Like these are the AB terminals. If you have seen through these two terminals, the admittance, the equivalent admittance seen through these two terminals is YAB of omega. So here the admittance seen through the terminals AB can be written as, what is YAB of omega in terms of conductance and susceptance? So GAB of omega plus J times BAB of omega. So this is the conductance, is it? And this is the susceptance. So this is the reciprocal of resistance. This is the reciprocal of reactance. Then this network can be replaced by a current source IN of T with power spectral density 2 kT GAB of omega in parallel with the admittance YAB. So this is the GAB of omega and this is the J into BAB of omega. I redraw this. That is where this is the simple extension of the previous case. We considered single resistor that is replaced by a noiseless conductance in series with, noiseless conductance in parallel with the current source, noise current source. We are doing the same, but we are generalizing the process. So this particular network may consist of more than one resistor. So this is a generalized linear passive bilateral network that may be having more than one resistor. So here we find the admittance seen through the terminals AB, and then this network can be replaced by a noiseless admittance. So this is a noiseless admittance, that is GAB of omega and J times BAB of omega is a noiseless admittance in parallel with a noise current source with power spectral density 2 kT GAB of omega. That is, according to the generalized Nyquist theorem, these two circuits are equivalent, or these two networks are equivalent. What is this GAB of omega? That can be written as the real part of YAB of omega. That is the conductance seen through the terminals AB is given by the real part of admittance seen through the terminals A. So this linear passive bilateral generalized network consisting of RLC components can be replaced by a noiseless admittance. Okay, this is the combination of these two is the noiseless admittance in parallel with a noise current source. Can you draw the Thevenin equivalent of this? That is, the same network can be replaced by a noiseless impedance ZAB of omega in series with a noise voltage source Vn of t with power spectral density 2 kT RAB of omega. Why RAB of omega? This ZAB of omega, that is the impedance seen through the terminals AB, is given by RAB of omega plus JXAB of. So therefore, this RAB of omega in this case is the real part of ZAB. So this circuit is the Thevenin equivalent of this. So I can also draw this. This is R. What is this? This is J into XAB of omega. They are in series. So therefore, this network can be replaced by this. A generalized linear passive bilateral network can be replaced by a noiseless impedance in series with a noise voltage source with power spectral density 2 kT RAB of omega. Here, the same network is replaced by a noiseless admittance in parallel with a noise current source with power spectral density 2 kT GAB of omega. So this is the generalized version of the single resistor case. Find the power spectral density of noise voltage across AB terminals of the network shown. So this is a given network. You have to find the power spectral density, the PSD of the noise voltage. See, we have two noise sources here. That is, we have two resistors. Each resistor acts as the thermal noise source. So definitely, the voltage across these two terminals will be a noise voltage. You have to find the PSD of this Vn0 up. For that, first what you have to do? You have to replace the network by its equivalent. What is YAB of omega? So 1, is it right? Admittance seen through the terminals AB. What is the admittance seen through the terminals AB? This is YAB of omega. So YAB of omega is 1 plus j omega into 1, because capacitance 1 here, plus 1 divided by 2 plus j omega. Is it right? What is the impedance of this branch? Impedance of this branch is 2 plus j omega L. So that is 2 plus j omega 2. admittance is 1 by 2 plus j omega. Here the impedance is 1 by j omega c. So admittance is j omega, and this is 1. 1 by 1 is 1. Find the ZAB of omega from this. So 1 by YAB of omega. So once you know the ZAB of omega, from this we can find the RAB of omega. Is it? RAB of omega is the real part of ZAB of omega. So if you know the RAB of omega, what is the power spectral density of the voltage across the output terminals AB? That will be equivalent to 2 kT or AB of omega. We already know this. Find the ZAB of omega, that's the reciprocal of this, then find the real part of ZAB of omega. Therefore, the power spectral density of the voltage across AB is given by 2 kT RAB of omega. Alright, you find this RAB of omega and substitute, you will get SV of omega. Here I written the subscript V that indicates the power spectral density of the voltage. If I ask you to find the power spectral density of the current, you will get 2 kT GAB of omega. So GAB of omega is the real part of YAB of omega. Similarly, find SI of omega also from this. What is SI of omega?